There's different ways to represent the electric field. I've heard this on Thursday, but basically there's the vector field one where you're assigning an arrow essentially to every point in space, and then field lines. Lines, it's sort of like lines of force. It's easier to just see it in action. So that's why this website, flashphysics.org, it's great. Take a minute and just think the electric field. Oh, why is that happening? Yeah, the electric field over here to the right of this positive test charge, in what direction does it point? What about up here? What about to the left? And what about down here? Over here, it's to the right, it's up, it's to the left, and it's down. And why is that? Just remember, we define the direction relative to what a positive test charge would experience. You can see over here, it's experiencing force to the right, over here, force up, to the left, down, etc. So that's a positive test charge. What about a negative test charge? Think about it for yourself. Direction of the electric field here, there, there, and there. So you can see it. It is basically the same, except it's pointing towards it because positive test charges would be attracted to this negative. So what does the vector field representation look like? It's just a bunch of arrows pointing towards it. And this is a nice little website because you can show the field lines as well. Field lines don't have the arrows on them, but you can kind of see it's, symmetrical. Okay, so that's positive. I just want to do the positive again. The field lines and the field vectors like that. What about for a dipole? Think about it for yourself. In what direction is the electric field pointing over here? What about over here, over here, and over here? Let's find out. This is an important example. I don't know if you can see it, but just to the tip of the mouse pointer, there is a tiny arrow to the right, and then there's a big arrow to the left, and then the resultant is to the left, which is the bright yellow line. The electric field is a vector. So I'm getting a contribution from this guy and from this guy at this location. The positive test charge is pushing to the right. The negative the positive source charge is pushing to the right. Let me rephrase. The positive source charge, the electric field from it at where the mouse pointer is pointing to the right. The negative source charge at the pointer's location, the electric field from it is pointing to the left. But the negative charge dominates because it's closer. And so the resultant, when I add those two vectors, is to the left. And you'll get a similar scenario on the right. You'll see the tiny little arrow to the right is from the negative source charge. The electric field from that is to the right, but it's far away, so it's smaller. So when I say solving simple quantitative problems, I mean being able to add those together. KQ1 over R squared, the distance between the positive and this location, and then negative and this location. And then subtracting those numbers because those numbers, like those electric fields, are pointing in the opposite direction. That's really what you should be able to do. Up here, you can see the two individual field vectors nicely, and the resultant is in bright yellow. And then down here, it's a similar story. The positive test charge would feel a force down and to the right from the positive source charge. The positive test charge would also feel a force up and to the right from the negative source charge. Cool, cool, cool. So here's the field vector representation, and then here is the, and then here's the field lines. Very, very aesthetic. So that was two opposite charges. What about two charges with the same sign? Think about it for yourself on your own. In what direction is the electric field pointing over here, over here, over here, and over here. So you can see the closer one dominates. Actually, they're pointing in the same direction here. And over here. And over here, they're pointing in opposite directions. So that's why the net field is down. And over here, the net field is up. So those are the field vectors basically pointing towards them. And the field lines kind of show you the shape. Very, very static. Okay, that was that. And then the last one is a row of positives and a row of negatives. Where do you think the field vector points? Over here, here, and here. Take a minute. It points straight up throughout. Basically, all the horizontal components cancel out. And so if you were to look at the field lines inside, they're just straight lines. Don't worry so much about the outside. The outside's not important. And the field vectors. Key idea, inside, it's pointing all in the same direction and is actually a uniform field. And those are the basic charge configurations that you need to know, and the field line representations and the field vectors. I invite you to play around with the website. In summary, the electric field strength, it's what a positive test charge would feel if it's at that location. Key idea though, there is no actual test charge there. You're just imagining it. And those are the common representations. This is my electric fields video. Hopefully it was helpful. Work out the practice and check out the solutions. That should help cement the ideas a little bit. Take care.